All right, so today we're talking about momentum and impulse. So, momentum is basically a way of giving value to the amount of inertia that an object has when it's in motion. In sports, we often hear them say things about a team having momentum and meaning that they're on a roll and it's going to be a really big challenge for their opponent to stop them or slow them down or overcome them and win the game or something to that effect. So, momentum in this case is talking about just the fact that they're playing really well. They're kind of like on a roll. But in physics, momentum is an actual measurement of the mass of an object and the velocity or speed with which the object is moving. So, momentum is going to be based upon the object's velocity, and this means that momentum is going to be a vector. Whatever direction the velocity is, that is the same direction that the object's momentum will be. We calculate momentum using the formula P equals m times v. So let's just take a moment to review what our unit should be for our variables. Mass is going to be measured in kilograms. Velocity is measured in meters per second. And this letter P, this lowercase p, seems kind of random, but that is the letter that we're going to be using for our momentum. And so when we look at our units for mass and velocity, we get kilograms and meters per second. And there's nothing to simplify there. There's nothing that cancels out. And so we're actually going to leave our answer in a unit of kilogram meters per second. If we are looking at the formula for momentum, we say P is equal to m times v. So if my object were to experience any variation or change in its momentum, it has to be either because the mass of the object has changed or the velocity of the object has changed. So here in the first example, it says as velocity increases, momentum increases. Now, this would be a true statement, assuming that the mass of the object does not change. So here in our example, you see that we have an example of a car or of some sort of vehicle that is hydroplaning while driving 20 miles per hour versus 70 miles per hour. So in this case, it's the same vehicle that is experiencing this motion. It's just that the vehicle is moving at different speeds. So our mass is the same for these two situations, but it's just the velocity that has changed. Now, if you just think about experience, whether you are the one with the experience driving or maybe you just have experience as being a passenger in the vehicle, but we should understand that if I am driving and I'm going 20 miles an hour and I hit a patch of ice, or I hit a patch of water where my car loses traction and I no longer have control, you should understand that moving at 20 miles per hour gives you some momentum and your car is going to continue sliding or moving or whatever direction because of that momentum. But if I'm going 70 miles an hour, now I have so much more momentum. My car is going to continue moving and it's going to resist changing its motion. It's going to show that path of inertia much more strongly because I have more momentum because of my greater velocity. In the second example, we have a mass that has changed, and so if we change the mass, then the momentum also changes. So increasing the mass increases the momentum. Now, this would be a true statement, assuming that the velocity has not changed for our two situations. So if we look here at my example, we are actually not talking about the same object. In these two situations, we are actually comparing two objects of different masses. So here we are comparing a motorcycle, which would be a small mass, moving at 60 miles per hour, to an 18-wheeler semi-trailer, however you want to say that is going 60 miles per hour. So obviously here we have two different masses, both moving with the same velocity, but we understand that the semi-trailer or the 18-wheeler definitely has more momentum because of its inertia and the speed at which it is traveling. It is going to be more difficult to bring it to a stop or to change its speed compared to the smaller motorcycle. So now we have a question. Can a rollerblader and a 1-ton truck ever have the same momentum? And the answer to this question is yes. Now, technically, yes, if both objects are at rest and they both have zero momentum, so that would be a situation where my objects would have the same momentum. But in this case, I'm looking for an answer where my object is actually moving with some velocity. So in order for these two objects to be moving but still have the same momentum, then this means that my more massive object must be moving with a very slow velocity, and at the same time, my very small mass object should be moving with a large velocity. Okay, so it is possible, but it has to be under the right circumstances. All right, so now we're going to look at an example problem of just calculating momentum. So you can see here that we are being asked to calculate momentum. So P equals question mark is what we are solving for. This is the mass. So I have a 65 kilogram sprinter, and my sprinter is running at a velocity of 10 meters per second. So my formula is P equals mv. So 65 times 10 gives me 650. Now, let's just make sure that we understand some things. We said that momentum is a vector and it's going to be in the same direction as our velocity. So reading through this problem, we see that our sprinter is running to the east. So this means that my velocity is a positive value. Therefore, my momentum that I calculate is a positive value. So my complete answer here would be P equals 650 kilogram meters per second as a positive number. If my object were moving west, then my velocity would be negative and my momentum would need to be expressed as a negative value. Remember that momentum is a vector. So as we move forward in the chapter, we can't forget that we must include the correct positive or negative sign to our value so that we can represent this momentum correctly. All right, so changing momentum. We did a lab where you held a ball at various heights, dropped it, and observed the ball hitting the ground and then bouncing back up. Now, our focus at that time was comparing the amount of potential energy at the highest point, and then understanding that transfers to kinetic energy, and then it bounces back up to a second height. And in that case, we were analyzing how the second height was not as great as the first, and we understood that we lost some of our energy to thermal energy whenever the ball contacted the ground because of friction. What if, instead of analyzing the differences in energy, we were analyzing the momentums? We would need to understand that if we could find the velocity at the different moments, then we could easily calculate the amount of momentum that the object has. So what we would find is that the momentum of the object changed. So now let's talk about why did it change? What caused it to change? In this case, the mass of the object obviously stayed the same, but the velocity was different. So what created that change in velocity that ultimately caused the change in our momentum? So if we're looking at our objects here in this picture, we have a teddy bear and we have a ball, and they are being dropped so that they both are falling with some velocity. And then we can see in the after picture, the teddy bear comes to rest on the floor where the ball is actually going to bounce back. So in this case, instead of moving down towards the ground, it's going to bounce up towards the sky with some velocity. So the question here is, which object experiences the greater magnitude of momentum change? So we don't have numbers here, This is intended to be a conceptual question. So conceptually, I want you to interpret this question. We're seeing that we have v for our velocity for both the teddy bear and for the ball. And they don't give us any numbers, so I want us to interpret this question saying that we have the same velocity for both of our objects, okay? Now, to make it a little bit easier to understand, we're going to go ahead and we're going to put up some values. Now, remember, this is a strategy that you can use at any time if you are trying to make a comparison and you're just not quite able to visually understand what's happening, or you're just struggling to wrap your head around what is supposed to be the comparison. Make up numbers, it's totally fine. So we are going to say that our objects, in this case, both have a momentum, and we'll just go with 10 kilogram meters per second. Just totally made up this number, okay? Whoops, kilogram meters per second. Now, my object is going to fall, and we can see in this after picture, my teddy bear has obviously come to rest. So now this bear has a momentum of 0. It is mass times velocity. Velocity is 0 because it's come to rest. So my teddy bear experienced a change in momentum. And remember, change in anything is always going to be final minus initial for that variable. So to calculate the change in momentum for my teddy bear, I simply need to plug in what my initial and final momentums were. Now remember, velocity is a vector, therefore momentum is a vector. So if we look at the velocity of my bear, we have to decide, is this going to be a negative velocity or a positive velocity? Well, I'm just going to tell you what my students normally would say. This arrow is pointing down, and so they would typically choose to make this a negative direction for my velocity. Therefore, my momentum here would be a negative 10 kilogram meters per second. So when we go to do our math, we would say our change in momentum, specifically for our teddy bear, is going to be final momentum minus my initial momentum. So in this case, I have 0 minus a negative 10. So my teddy bear experienced a change in momentum of 10 kilogram meters per second. Now if we look at the bouncy ball, the change in momentum for the ball is also going to be final minus initial. So when we look at our initial, we've already established that's a negative 10 because we're going to say our velocity is in the negative direction. But let's look at our after picture. This ball does not come to rest on the ground. Instead, it bounces with a velocity. And if we're interpreting these velocities as being the same magnitude, because they're all expressed with just a v, then that means that this bear has the same momentum that it had before, but it's now in the opposite direction. Obviously, the mass didn't change. Momentum is mass times velocity. So if it's the same mass and it's the same velocity, then it should once again have a momentum of 10. But if we say that this was the negative direction initially, that makes this velocity in the positive direction. So my momentum after would be a positive 10 kilogram meters per second. So when we come to plug our numbers in over here, we would say final minus initial, which is going to give me a value of 20 kilogram meters per second. So the question once again says, which object experiences the greater magnitude of momentum change? And in this situation, the ball experiences a greater amount of momentum change. The teddy bear changed by a value of 10. The ball changed by a value of 20. Another way to think about this is that the ball kind of went through 2 changes in momentum. It experienced a change in momentum so that it had some velocity or momentum downward, came to a stop briefly, and then had an additional change where it then experienced a change in momentum because it began bouncing upward, right? So whichever way you want to process that. Here is the full image, and they basically are showing you the same concept that I just explained. We need to identify what direction our object is moving initially. So honestly, if we wanted to, we could have said that our teddy bear or the ball is moving forward and given that initial velocity a positive value, and then had it bounce back in the opposite direction that it was originally moving and had our final a negative. The math work still would have come out to be the same. All right, so what is responsible for creating a change in momentum? Well, remember, all objects have inertia, and they're going to continue doing whatever it is that they're doing unless we have some sort of net force acting on it to cause it to accelerate. So it's no different here. What causes a change in momentum? A force. Just like all other changes, it has to be because a net force was present. So if a force is present, then it's going to cause the object's momentum to change. Now, I am going to need you to understand the specifics and the vocabulary that we've reviewed before, how that is going to come into play for our momentum conversation. So let's go ahead and review that real quickly right now. Newton's second law is the law of acceleration. And it is the formula that says the net force is equal to the mass times the acceleration. Now, we talked about how the acceleration would be expressed as force divided by mass because that's what's going to determine the rate of acceleration. But this relationship in general is what we're going to use in order to determine how my object's momentum has changed, or why it changed, or what that magnitude of change should be. The definition of acceleration. In our very first chapter, we talked about acceleration, and we said that this is the rate of change in velocity. And so we had a formula that said acceleration is the change in velocity that takes place over time. So if we wanted to, we could take this formula and rearrange it for our change in velocity or for our time. So keep that in mind because we're going to come back and do that here in a minute. In general, if the velocity or the mass changes, then the momentum of my object changes. So if we're talking about a single object, obviously it's not the mass that's going to change, it's going to be the velocity. And so this must be because a force acted on my object in order to create that change. So a force acting on an object creates a change in velocity, which creates a change in momentum. The greater the force, the greater the acceleration, the greater the change in velocity and the change in momentum. Now it says here that time is also important. The same amount of force exerted on an object for a greater amount of time is going to create a greater change in momentum. Okay? This brings us to our new vocabulary word for the day. It is impulse. Impulse is the product of an external force and time, which results in a change in momentum for a particular system. Now we'll talk a little bit in more detail about what a system is in our next lesson, but basically the system is our object that we are analyzing and the environment that it's in, okay? So if we are talking about a single object, that object receives a force for some amount of time. That force is responsible for creating an acceleration. So the momentum is going to change because of the new velocity, and the amount of time that that force is being experienced is going to also affect how much or how little change in momentum the object experiences, okay? So our symbol for impulse is either going to be a capital J, or we're going to express it as a delta P, because our impulse is what creates the change in momentum, and we're going to learn through our practice work that those magnitudes are going to be the same, okay? Some texts are also going to use a capital I for the impulse. So you may see that from time to time. I will most likely use our delta P most often because I really think that that's going to be helpful in reminding you that the impulse is the same as the change in momentum. Our unit for impulse can either be Newton seconds. If we look at this definition up here, our impulse is the product of force times time. So newtons times seconds would be an appropriate unit for our impulse. If we understand that it is a change in momentum, and a change in momentum is final momentum minus initial momentum, then it could also be expressed as kilogram meters per second. If we were to stop and do the algebra and think about what a Newton is, mass times velocity, mass times acceleration, so kilograms times meters per second squared. Obviously, our unit for time is seconds, and if we were to look at that algebra and analyze what we are doing with our units and simplify that, we would find that these two sets of units are indeed equivalent, okay? Then it says here that our definition, our formula by definition, is that the impulse is equal to the force times time. And so we're going to use this relationship in order to help us work through some problems. We're going to need to connect the dots a little bit, but it all comes down to understanding that momentum is mass times velocity. A change in momentum for a single object would be because the velocity changed, and it had to be a force applied for some amount of time in order to create that change. All right, let's talk conceptually real quick. If your car is going out of control, you're driving and you've lost control and you're thinking, oh my goodness, I'm going to crash. What am I going to choose to crash into? If I swerve this way, I hit a brick wall. If I swerve this way, we'll say it's fall and there's bales of hay for decorations for the fall, right? So if I swerve the other direction, then I'm going to crash into a bale of hay. Let me clarify something. You're moving with some velocity, you have some momentum. Whether you choose the brick wall or the bale of hay, you're going to come to a stop, okay? So both situations will represent the same change in momentum because you're going to stop. You're going to lose all of the momentum you have. Well, if I have to crash and I get to make a choice, I'm going to choose the haystack. Now, why would I choose the haystack? A lot of times students want to tell me because the haystack is softer. But let's think about this in terms of the vocabulary that we're discussing today. I would receive a lesser force to bring me to a stop if I were to crash into the bale of hay, because coming to a stop with the bale of hay is actually going to take more time. Now, I understand that both of these things are going to happen very quickly, so it's a short amount of time regardless. But in comparison, it's going to require more time to bring my vehicle to a stop if the bale of hay stops me compared to a brick wall. A brick wall is going to give me a much more sudden stop, a lesser amount of time, which as a result means there must have been a really strong force in order to stop me. So from this conversation, what I hope you understand is that force and time are inversely related. Now, please understand, for both of these crashes, my change in momentum is going to be the same. Let's say that I'm driving with 1,000 kilogram meters per second initially, and I come to a stop. So my formula is going to be final minus initial. So in both cases, my change in momentum is a negative 1,000 kilogram meters per second. Assuming that it's the same magnitude, allowing me to come to a stop in more time as a result decreases the amount of force needed to stop me, okay? So this is a relationship that you'll need to understand in order to answer some conceptual questions. If you are being asked to calculate what is the force needed to bring me to a stop, how much time will it take, simply using this relationship of change in momentum, or impulse is force times time, this is the relationship you need to answer that question. Here are some other examples of the impulse change in momentum theorem. So when you jump down, let's say that you're jumping from a wall, or you're jumping off of, I don't know, the desk or a table, and you're jumping down off of some sort of surface, right? When you land, you are going to bend your knees. Ideally, you're going to want to bend your knees. So we know if you are an athlete, or if you've ever done any kind of jumping exercise, then you know from experience that it is ideal for you to bend your knees. That's going to cushion your landing, right? That's what we often say. Well, really, what's happening is when you bend your knees, you are giving your body more time to decelerate. So, by increasing the amount of time that it takes to bring you to a stop, you are decreasing the force that you experience on impact. Okay? Airbags are now standard in vehicles because airbags are going to give your body, your head specifically, more time to come to a stop. Therefore, there is a lesser force needed to decelerate you from moving forward, right? Crumple zones in cars, if you look at accidents nowadays, it looks sometimes way more severe than what it is, because the car is just all crumpled up in the front. The front of the car is just all squished and super damaged, but that's actually intentional. Cars used to be built with really sturdy bodies, very strong, heavy metal, and so whenever car accidents would take place, those accidents would happen in a really short amount of time. The metal on the vehicles did not give, and so it was a really strong force in order to bring it to a stop, because it happened like instantaneously. Now we have learned that if we create vehicles that are designed to crush or crumble in the front, it actually increases the amount of time that it takes to bring the car to a stop. So what that does is it causes a lot of damage to the front of the car, but it lessens the force that's actually being exerted to the vehicle. So the passengers inside of the car have more time to come to a stop, less force upon impact, and so that's going to be beneficial for the people involved in the accident. Follow through on a swing. Okay, if you have ever been coached to kick or hit something, then you've probably been instructed to follow through. Now, why do coaches ask you to follow through? It's not so that you can hit the ball harder. I know that's what a lot of people probably are thinking. This is a situation where we are looking at our impulse is force times time, right? Where the change in momentum is going to take place because a force was applied for some amount of time. But in this case, let's say, and really ideally, if you're trying to get the maximum result from your kick, hit, or swing, you really should be exerting the greatest amount of force possible. So let's say that we are exerting the same force in all situations, okay? Let's say that it's a full swing, kick, whatever, hit in every situation. So if our force stays the same, then if I follow through, what I am doing is I am increasing the amount of time that that force is being applied to the object. And so as a result of that, increasing the amount of time of contact is going to increase the change that my object is going to experience in its momentum. And did the mass of the object change? No, it did not. It's the velocity that changes. So what we see when we follow through, when we coach people to follow through on their kick or swing, is that the ball goes flying off the bat, foot, racket, whatever. Well, that's because we've increased the time, which has increased the change in momentum, okay? So, can you take this relationship of the change in momentum, final momentum minus initial momentum, and derive from that this relationship down here of delta P is equal to Ft. Well, let me remind you, we've already reviewed F equals ma, and the acceleration is defined as change in velocity over time. We're going to need those formulas to help us make this connection, okay? So we are saying that a change in momentum can be calculated by doing mass times velocity, which is going to give me my momentum. So mass times velocity final minus mass times velocity initial. Basically what we are saying is that our momentum has changed because the mass stayed the same, but my velocity changed, right? That's what this VF minus VI tells me. So my change in velocity means that my object experienced an acceleration, right? Now, if we come over here and we look at this formula and we solve or rearrange for a change in velocity. So let's take that equation and let's rearrange that. I'm going to multiply both sides by t. So my change in velocity is equal to acceleration times time. So now let's go back and plug that into our formula. I'm going to take this delta V and I'm going to replace it with acceleration times time. So that makes my equation that my impulse or my change in momentum is mass times acceleration times time. Now, we already came over here and we looked and saw that force is equal to mass times acceleration. So this mass times acceleration can now be replaced. Mass times acceleration is equivalent to a force. So force times time is equal to my change in momentum, okay? Now, ideally, you have a very strong understanding of the vocabulary, velocity, acceleration, force, and you already understand these relationships. I'm just showing you how to connect the dots and understand that as you work through your practice problems, you may need to pull any of these formulas and old relationships along with some of our kinematics equations that we've used in the previous chapters as well to help you work through the problems. All right, here I have a sample problem that I'm going to work. I'm not really super concerned with actually executing the math for you. Ideally, at this point, you guys are capable of executing the math. I just want to talk really about the relationships that you need to understand and kind of the process that you would follow in order to answer a question like this, okay? So here it says, suppose we have a 1.5 kilogram brick and it is dropped, so my initial velocity is 0. It is dropped onto a glass table from a height of 20 centimeters. And remember, we would need to convert that into meters. So this is going to be our height, or maybe it's going to be our displacement, but keep in mind it is in the vertical direction, okay? So the first question is, what is the magnitude and direction of the impulse necessary to stop? So our final velocity is 0. The brick, so the impulse is the change in momentum. It could be calculated as force times time, but we don't have that information. It does represent a change in momentum, which would result from the change in velocity that an object experiences. And so as you look at the variables that I've identified for us, we could absolutely use the change in velocity concept here, okay? Now, it says here that it's dropped. So we have an initial velocity of 0, and then I have a final velocity of 0. So wait a minute. It was moving at some point. I can't use VI and VF as 0. So let's think about what is happening. I'm going to draw a picture. So my object is dropped from some height and it falls. Well, we just finished learning about energy, and I understand that up here it has no velocity, so my kinetic energy is 0, but it has some height, so it has a gravitational potential energy, which can be calculated using mass times gravity times height. When it reaches the ground, it now has a potential energy of 0 because gravitationally it is at ground 0, so a height of 0. So all of that potential energy was now converted into kinetic energy. So we know that it must have some velocity here. So what we would need to do is first do a calculation where we know that the potential energy at the top is transferred to kinetic energy at the bottom, and we would actually need to calculate our velocity when it reaches the glass table. Okay, so this velocity here would actually serve as our initial velocity for our calculation. When we try to find the change in momentum, it's going to be final minus initial, where we're going to take the mass times the final velocity, which would be 0. This final velocity is going to be 0, minus mass times the velocity initial, where it would be this velocity that we found when it reaches the glass table. That would serve as my initial velocity. The difference between the two would be the impulse, or change in momentum, that the object experienced, the brick experienced. And the next question, if the tabletop doesn't shatter and it stops the brick in 0.1 seconds of time, what is the average force exerted on the brick? So at this point, we've calculated the change in momentum from the previous question. It's telling us that we have a time of 0.01 seconds, and they are asking for the force needed in order to stop the object. So this would just simply be that my impulse is force times time. I would just divide both sides by time, and I would calculate my force from that relationship. The last question here is asking what is the average force that the brick exerts on the table during this period. So this question is saying that we have a brick and it's going to land on a table. So we have calculated up here the amount of force exerted on the brick. The table is responsible for bringing the brick to a stop. So the table is going to apply a force upward onto the brick. The brick is in contact with the table, so it's going to give an equal force but of opposite direction. So the magnitudes are the same, but the direction is opposite. So this means that the force applied onto the average force that the brick exerts onto the table is going to be the same magnitude that the table exerts onto the force, but in the opposite direction. And once again, this is because of Newton's third law. Okay, so our answer here would be negative F, whatever F was in the previous question. All right, the last thing that we're going to look at is interpreting impulse from a graph. So this is a force time graph. So if we look at our X and Y axis, the X-axis represents our time, and this is in milliseconds. Our force is measured in newtons, and that's going to be our Y-axis. And so you can see here that we are telling you that if you find the area under the curve, this is going to give you the impulse. So real quickly, you might be wondering, why is there more than one value represented for the force on this graph? Well, technically, upon impact, the force changes as the object comes into contact. The force that is being exerted onto the object changes because technically, if we just picture, or if you've ever seen some sort of crash or impact in slow motion, there is kind of a progression of impact where there is a moment where the object is fully pressed against whatever surface it is hitting. And then we, especially in the situations where we have balls that are going to bounce back or something like that, then we have the compression of the ball, and then that force is then decreased as the ball begins to lift up off of the ground or lessens its contact, right? So we end up with a graph that's not necessarily a constant or steady slope in a lot of cases. So here we are telling you that if you find the area under the curve, this is going to represent your impulse. And let's talk about why that is a true statement. How is that so? Well, if we look at the area that we have here, this particular example, we are trying to find the area of a triangle. So if we recall the formula for the area of a triangle, this is 1/2 base times height. Now, if I look at my graph, my base is going to be a variable of time. My height, or the y-axis, is going to be the variable of force. So if I were to rewrite this, base is time, height is force, force times time is my impulse. Now it's 1/2 base times height because the shape is a triangle, okay? If you were to be given a graph where we have, maybe we do have a constant slope for some amount of time. If we were trying to find the area for this section, this would be a rectangle. So the area of my rectangle would just be base times height, but once again, this is simply force times time, okay? If we were to get a question where we're given some sort of graph where maybe it does like this funky thing where it comes up and then it goes over and then we have like a peak and then it comes down. How would we find the impulse for this type of graph? Well, we would basically just have to divide it into sections. We'd calculate that area of that triangle, we'd calculate the area of this triangle, and then we would see here that we have a rectangle. We'd calculate this area, add them all up, and that would be our impulse, okay? So then the last thing that we're going to look at for today's notes is an example of how we would actually calculate this and how would this be useful for our conversation of momentum. So in this example, it says that we have a force that acts on a 1.2 kilogram object. So here is our mass. The object is moving with a velocity of 120 meters per second, and it says the direction of the force is aligned with the velocity. This just means that the force is in the same direction as the velocity, so it'll be a positive force for us, which means the impulse is positive, which means the change in momentum is positive, okay? So the question that they're asking is, what is the new velocity of the object? So this question wants us to solve for the final velocity. So we should understand that the change in momentum is going to be mvf final minus mv initial, and we are solving for this final velocity. Okay, that's what the question wants us to do. So in order to calculate that final velocity, I have all of these variables on the right. I don't have a value for my change in momentum or my impulse here on the left, so I'm going to find that. So the way that I'm going to find that is I'm going to look at this graph and I'm going to see that my units are force and time. So if I simply find the area under this slope, that is going to give me my impulse. So I'm going to say that my impulse is 1/2 base times height. So my change in momentum is going to be 1/2. And then on this graph, my base is 0.4 to 0.5. And my force is from 0 to 2,500. And so this is how I would set up my problem. Once I calculated my change in momentum or my impulse, then I would be able to take that value and plug it into the relationship of mass times velocity final minus mass times velocity initial, and I would just do my algebra here to solve